Okay, let's take a look at some of the substitution reactions. You're given an alkyl halide which is being treated with water. Notice the nature of this alkyl halide is that it's a secondary alkyl halide, and what you're reacting with it is polar protic solvent, polar protic. So that should tell you that it's going to be SN1. That should tell you that you need to form the carbocation first. So let the bromine go, giving you a positive charge. The double bond is way too far away, so you can't show any conjugation or any resonance in this case. And now you will simply use the water to attack from the top or from the bottom. And so you're going to first show the formation of an OH with a positive charge, plus, since it's a racemic mixture, and then another molecule of water, or the Br, can pick up that proton, release the positive charge. So you're going to end up with a racemic mixture containing the alcohol at the secondary location via an SN1 route. Alright, let's take a look at the second one. We have, again, a secondary halide. We are treating it with NaCN and DMSO. CN minus is a good nucleophile. DMSO is a polar aprotic solvent. Polar aprotic. And that means it has to go through an SN2 reaction mechanism. That means the attack and the loss of bromine both will occur at the same time. You cannot quite show carbocations. So loss of bromine, several of you wrote just Br. It has a negative charge. And the incoming Cn minus, which also has a negative charge, by the way. Carbon has a positive charge. So that's your transition state, and when it materializes, you would get, in this case there is no chiral center, but if you can show that, pointing down, that should be good. All right, and NABR, of course, is your side product. All right, let's go forward. Okay, so another one that's given here is an alkyl halide, which again is a secondary position, and we are treating that with CSI, that means I minus, which is a good nucleophile, but it is being done in methanol. So realize it's not necessary that you can have a good nucleophile by itself. You can absolutely use a polar protic solvent at that, and so the reaction in that case is going to go through an SN1 reaction mechanism. And so you would show the loss of Cl. That will give you the formation of the carbocation, and now that hydrogen can actually move to give you a more stable and achiral carbocation, and so you will get 4 products total. Actually, the I minus can attack top or bottom in both the cases, so you would have a racemic mixture at the secondary center, and really this one is achiral, so just iodine at that location. We have the same substrate, and now I'm treating that with KOH. Since no solvent is provided, the incoming nucleophile, which is hydroxide, has to decide whether it's going to be SN1 or SN2. You'll base off that. So that's SN2 because it's a good nucleophile, so it'll support that more. And so the attack and the loss should occur at the same time. So you can show Cl delta minus, delta positive, and the OH delta minus coming in. And your product then is going to be OH at the back side, really, so dash line. And that's an SN2 reaction mechanism. Okay, we had to now rearrange or rank H2O, hydroxide, and acetate in accordance to their nucleophilic character, basic character, and the third one was the leaving group capability. So first things first, let's talk about nucleophilic behavior. First of all, negative nucleophiles are stronger than neutral. That means both the hydroxide and the acetate should be more than water. So water is least. And then within hydroxide and acetate, realize acetate has resonance, so that charge is actually spread over the oxygen atoms as well. Hydroxide has most negative charge, and so that will be the order of the nucleophilicity. The basic character, if you wanted to compare that, you should just compare the corresponding acids. So if the acids are strong, the conjugate bases would be weak. So we are saying we are comparing hydronium ion, water, and acetic acid. And so hopefully you can see that hydronium ion is most acidic and H2O is least acidic. And that would mean that the strongest base will be hydroxide. That will be the strongest base. And weakest base will be water, and acetate will be in between. So the order will be OH negative, CH3, COO minus, and H2O. This, of course, is based off what you know from general chemistry 2, that Ka times Kb is a constant Kw. If Ka is high, Kb will have to be low. Alright, let's take a look at the leaving group capability. And I have told you, in order to figure that out, you should just basically pay attention to what kind of conjugate acid you have. So in case of water, hydronium ion. In case of hydroxide, I have water. In case of CH3COOH, I have acetic acid. And then the rule is greater the conjugate acid, greater will be the leaving group capability of that particular component. That means water should be the best leaving group, followed by OH negative, followed by acetate, followed by OH negative. Okay. We then had to do the same thing for bromide, chloride, fluoride, and iodide. So again, realize that down in a group, nucleophilicity increases because polarizability increases. So down the group, nucleophilicity increases since polarizability, or the size, increases. So essentially that iodine is going to be able to hold that negative charge better due to that big size. And so I minus is most nucleophilic, followed by bromide, followed by chloride, followed by fluoride. If you look at the leaving group capability, it follows pretty much the same trend, because the conjugate acid of I minus is going to be strongest. HF, you know from general chemistry 2, that the bond between hydrogen and fluorine is going to be pretty strong, and so that's not acidic at all. So both leaving group as well as nucleophilic character have the same order. Basicity, however, is going to be opposite, because since HI, the bond is weak, the bond breaks pretty quickly. That means that HI is a strong acid, and if it is strong acid, that means that the I minus is going to be the weak base. So for the basicity, and I'll just switch the color, fluoride is most basic and iodide is going to be least basic. Okay, and then a reaction was given that you have chloropropane, and you are treating that with sodium cyanide and methanol, and you end up getting this nitrile. And there were a couple of questions that if you change the Cl to I, what would be the effect? What would happen, so fast or slow? What would happen if you go from methanol to aceto to DMSO rather? And the third one was if instead of using 1 chloro propane if you use 2-chloropropane, so another isomer of that. How is that going to affect the rate of the reaction? Realize that if you are going from Cl to I, that means that you are making the leaving group better. And while since this is an SN2, hopefully you can identify that this is primary and it's a good leaving group. Because it's primary, it's a good leaving group. A good nucleophile, but because it's primary, you assign it an SN2 reaction mechanism, and so that is not really contingent upon your good leaving group, but it also, of course, it helps any substitution reaction if you have a good leaving group associated. So you would say that it is going to become faster, tad bit, but it would become faster for that reason. The next one is that you're switching the methanol to DMSO. Realize if it's a SN2 reaction mechanism, then DMSO, which is a polar aprotic solvent, is going to support that. It's going to support the SN2, and so that will be a fast reaction as well. And the last one is that you have 1-chloropropane to 2-chloropropane. So you're going from a primary to a secondary carbon. Sterically, this is going to be more demanding. And if it is more demanding sterically, it's going to basically become a slower reaction. Okay, I have another alkyl halide here, which is a secondary halide. I have a good nucleophile, and I have DMSO, which is polar aprotic. All of that is pointing towards an SN2 reaction. That means attack of the nucleophile and leaving group leaving will take place at the same time, and is going to give rise to an inversion of configuration such as that. You will not be drawing a full carbocation. The next one over here is again a secondary halide, but it's also at an allylic position. The reaction is being done in water. It's a good nucleophile, but because water is present and the allylic carbocation can get generated, let the bromine leave, because this is going to be an SN1 reaction condition, and that would mean that you would have two possibilities for the resonance stabilized carbocation, and now your I- can attack top or bottom to both of these carbocations, so your product will be a mixture of two racemic mixtures. And then the primary allylic, which is at a chiral center, so it doesn't matter. Okay, let's go forward. Alright, so again I have a secondary alkyl halide, and that's being treated with methanol. Methanol is your nucleophilic solvent, so it is going to go through an SN1 reaction mechanism. That means you're supposed to show carbocation, so let bromine leave. Let's get the carbocation. MEOH, methanol with the lone pair, can attack top or bottom, and so you're going to end up with the protonated methanol. The Br is going to come in, pick up the proton, relieve the charge, and that's your product. And of course, because it's racemic, the attack can take place in both the directions, and so the OME is going to point down. There will be another molecule where the OME is going to point upward. So you can just show that as the solid and the dash, and that's okay. That's a much better way of showing things. Alright, let's take a look at more problems. Another one that was given was that you have a Cl. I think this was in the other set also, KOH, Since nothing has been said about the solvent, I would go with the nucleophile, and I would say that this should be SN2. That means attack and loss of Cl is going to go through and give you OH pointing backwards. Now, if they would have said KOH and then given aqueous, then that would mean that that would be an SN1 route. In that case, you would have obtained a carbocation as the intermediate, and you should then take the time to show the hydride shift, which is going to give you a racemic mixture, which really is an achiral molecule like that. All right. Okay, the next question was that you have the alkyl halides, 3 different alkyl halides, primary, secondary, tertiary, and you had to tell what happens with sodium iodide and acetone, which one is going to be fast, and what happens when you change the solvent from acetone to water. Realize sodium iodide acetone is basically SN2 reaction mechanism, which tells you that primary halides are going to be the best, so I'm going to give that number 3. Tertiary is going to be the slowest, so I'm going to give that a number 1. And of course the secondary is intermediary. If you exchange that with sodium iodide and water, then in that case you're going to see the fastest reaction for a tertiary halide, because the carbocation is going to get generated pretty quickly, and the primary halide is going to get number 1. Okay, let's take a look at the last question. The question was that you have this compound, you're treating that with bromine. If nothing is written, that means they're doing it in some kind of an organic solvent. Water is not there. Water is a special case. So, of course, you will keep the methyl group as is. And you can have the Br if the bromonium gets generated pointing in that direction. And so the incoming bromide will point at the bottom. Likewise, you can draw another structure where this bromine is pointing down, this bromine is pointing up. And so the question was that you have to predict the products, you have to identify the chiral center with the absolute configuration, and then predict how many unique stereoisomers are formed in this reaction. So if you work on the priority, this is 1, this is 2, this is 3, and hydrogen is 4. So 1, 2, 2, 3. Looks like we are going R, and so this is R as well. Now for the 2 bromines, bromine gets the highest priority. This side gets the second highest priority. Likewise, this side gets a third priority. Again, 1 to 2 to 3 still sounds like we are going R, and that would mean that the bromine in the other direction here should be S. And now again I'm going to do the same thing. This is 1, this is 2, this is 3. We are going to go anti-clockwise, but the hydrogen is pointing towards us, so S is going to be switched back to R, and that makes this guy S. So my 2 combinations are R, 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 and R, S, S. Notice the question says how many unique stereoisomers are formed in this reaction. So this reaction gives you that anti-product. These are the only 2 combinations that are possible. Everything else is going to repeat itself over these 2. However, if the question would have been how many possibilities for this molecule, then you would say 2 to the power of n, and you would get it to be 8. But in this case, the only possibility is the bromine either coming from top or bottom, and then the ring open. So the answer to that is 2 in this case. All right, that is it.